Hey everyone, welcome back. Today we are cracking open the machine learning toolkit to get our hands on two of the most fundamental predictors out there, linear regression and decision trees. So let's dive right in.
It all really starts with a simple, practical question just like this. How do we teach a machine to predict something like a price? Whether it's a house, a car, maybe a stock. How do we get a machine to make a really solid, educated guess? Well, that's the puzzle we're going to solve today.
Okay, so here's what we've got on tap. We're going to start with the big picture, supervised learning. Then we'll get into our two main tools, the straight line approach and the branching path. We'll even peek under the hood to see how they actually make decisions, figure out how to grade their performance, and then we'll wrap it all up with a quick exam review.
All right, first things first, let's talk about the foundation. Supervised learning, it's pretty much exactly what it sounds like. We get to be the supervisor. We give the machine a data set that already has all the right answers. We call those labels. The model's job is just to learn the patterns, to figure out the relationship between the inputs and those correct outputs.
So you've got two main flavors of supervised problems. There's classification, which is all about predicting a category. Is this email spam or not spam? But for today, our focus is squarely on regression. And that's all about predicting a number, a continuous value, like the price of a house.
Okay, let's grab the first tool from our toolkit, linear regression. I want you to think of this as the ruler. It's the most straightforward, no-nonsense way to model a relationship. It basically assumes that as one thing changes, another thing changes in a nice, consistent, straight line.
And you can see what's happening here, right? The whole goal of this algorithm is to draw one single straight line, the line of best fit, that slices through the data and gets as close as it possibly can to all those little data points. It's trying to minimize the total error, which is really just the distance from each point to that line.
But how does it actually do that? Well, it all comes down to this equation. Here, y is our prediction. Each x is one of our features, like the car's age or its mileage. And those w values, you can think of them as weights. They tell the model how important each feature is. A big W means that feature has a huge impact on the price. And that B at the end, that's just the intercept, kind of our starting price before we even look at any of the car's features.
But what happens when the relationship isn't a nice, neat, straight line? For those more complicated, non-linear patterns, we need a tool that's a bit more flexible. And that brings us to decision trees. If linear regression is our ruler, a decision tree is like a flowchart. Yeah, so instead of one single line, a decision tree is all about asking a bunch of simple yes or no questions. Is the house bigger than 2,000 square feet? Yes? Okay, let's go down this path. No? Okay, we'll go down that path. And then it asks another question. This whole branching structure lets it capture way more complex patterns in the data. Okay, let's quickly break down the parts of a tree. We always start at the very top, at the root node. That's where all our data lives at the beginning. Every question it asks is an internal node. The answers to that question create the branches, which lead you down the tree until you finally hit a leaf node. And that leaf node, that's your final prediction. And the way it builds this tree, that's called recursive splitting. It's actually pretty intuitive. The algorithm just looks at all the data, finds the absolute best question to ask, and then splits the data based on the answer. Then it does the exact same thing on those new smaller groups, and again, recursively, until it just can't make any more useful splits. Okay, this brings us to a super important question, and definitely something you'll see on an exam. How in the world does the tree decide which question is the best one to ask? Well, it all comes down to some pretty clever math. So for the trees that are predicting numbers, our regression trees, the magic ingredient is something called variance reduction. Now, variance is just a fancy way of saying how spread out or messy a bunch of numbers are. A fantastic split is one that takes a really messy, high-variance group and divides it into two new groups that are way more consistent, way more predictable, you could even say boring. And that's the goal. So let's imagine we start with a group of house prices that are just all over the map. The variance is super high. Let's say it's 25.67. That number tells us that right now our data is pretty unpredictable. But then we ask a question, maybe something like, is the house in this specific neighborhood? And bam, our new subgroups are suddenly way more consistent. One group has prices all clustered together, and so does the other. Our new combined variance plummets all the way down to 0.67. And that right there is the key. The difference. We went from 25.67 all the way down to 0.67. That gives us a variance reduction of 25. The algorithm tries out a ton of different questions, and it will always pick the one that gives it the biggest drop, the highest variance reduction. So that's regression. But what about classification trees, the ones predicting categories? Well, for those, we use a different yardstick. Instead of measuring variance, we measure impurity. And this analogy is perfect. Think of the Gini index as an impurity thermometer. A score of 0 is perfectly pure, all one class. A score of 0.5 is total chaos, a 50-50 mix. The tree's job is to make splits that bring the temperature down. But there's a little catch here. What happens if a split gives us one really impure group and one that's perfectly pure? Look at this example. Subgroup A is as impure as it gets, Gini of 0.5. But subgroup B is perfect, Gini of 0.0. So, was it a good split? The key thing to notice is that the groups aren't the same size. We can't just average the scores.
And the solution, as you can see right here in this table, is to use what's called a weighted Gini. It's simple, really. We just take the Gini score for each group and multiply it by its weight, which is just how many data points ended up there. So that first group has 2/3 of the data, so its Gini of 0.5 gets scaled down to 0.333. The second group is pure, so it adds nothing. The final, fair score for the entire split is 0.333.
All right, so we've built our models, we've got our line, we've got our flowchart, but are they any good? I mean, did it actually work? That brings us to our final big step, actually grading their performance.
Well, for regression, we've got a few different ways to grade them, kind of like a report card. MAE, or mean absolute error, is the most direct. It tells you, on average, how many dollars off your price predictions were. MSE, mean squared error, is similar, but it really punishes big mistakes. And RMSE just turns that number back into dollars, so it's easier to understand. And finally, R squared is a bit different. It tells you what percentage of the price changes your model actually managed to explain. It gives you a sense of its overall power.
Okay, let's wrap this up and lock in all the key ideas. This is your exam review, so this is the stuff you really want to remember.
Okay, here's what you gotta know. Linear regression is your ruler. It's for straight line problems. Decision trees are your flowchart, using recursive splitting to handle the complicated stuff. For regression trees, the best split is the one that gives you the biggest variance reduction. For classification trees, the best split gives you the smallest Gini index. But, and this is a big but, the major weakness of a single decision tree is that it can overfit, meaning it learns the training data too well. The solution? Things like pruning the tree or using powerful methods like random forests.
So there you have it. You've now got two powerful new tools in your toolkit, the simple, reliable ruler and the flexible, intelligent flowchart. So my question to you is, what real-world prediction problem would you want to solve first? And which tool would you reach for? That's all for now. Keep learning, and I'll see you next time.